Assalamualaikum and greetings to Doctor. So me, SYAFIA, and my friend SILVIA will be presenting our journal topic, Public Health Surveillance with Incomplete Data, Spatial Temporal Imputation for Impairing Infectious Disease Dynamics.
Now let's proceed with the problem being addressed. We all know that infectious diseases are a major threat to mankind, and tackling them requires effective public health surveillance. But this isn't always easy, especially during an outbreak. Data is often missing, whether in certain location that is spatial missing, time period that is temporal missing, or random missing. This missing information makes it difficult to detect spatial and temporal patterns of disease transmission, which are crucial for timely response and resource allocation.
The objective of this study is first to address the challenge of public health surveillance while working with incomplete data in the context of infectious disease monitoring. Second is we need to develop a novel method, which is spatial temporal imputation via kernel-based learning, or known as STIKL, for impairing spatial temporal correlations using underlying risk factors and external information. The third objective is to accurately reconstruct disease spread patterns despite its missing data by leveraging the proposed STIKL approach. Lastly, they want to validate the effectiveness of the method through experiments on real-world malaria data and synthetic dataset while demonstrating its superiority over existing techniques.
Next, let's take a look at the methodology used in this paper. The proposed solution is the STIKL method, which stands for Spatial Temporal Imputation via Kernel-Based Learning. In simple terms, this method helps us fill in the missing data by finding correlations between risk factors and geographic location. It does this by looking at how risk factors change over time and across different areas. It then estimates the relationship using a kernel-based approach and use an alternating algorithm to continuously update and fine-tune its parameters for better accuracy.
In this journal, there are three types of data used. First is real-world malaria surveillance data, which is located at Tanjong Country, Yunnan Province, China. The data is collected monthly from 2005 to 2009 and is targeted specifically for the disease Plasmodium vivax malaria. This data is collected first by geographical location information, which is the latitude and longitude for each of the 18 townships in Tanjong Country. Second is 22 socioeconomic attribute for each town. The second data is vectorial capacity data. So this data is used to characterize the potential risk of vivax transmission. It was calculated based on its existing work and is related to per capita mosquito density, temperature, and fall. The last is synthetic dataset, where it helped confirm that the STIKL method effectively infers infectious disease dynamics from incomplete data. So it tests missing data scenarios such as spatial missing, which is where data is missing for entire periods in some locations, temporal missing, where the data is missing at specific time points, and random missing, where the data is missing across both spatial and temporal dimensions randomly.
Moving on to the findings, the researchers found that STIKL outperforms other methods on both real-world malaria datasets and synthetic data. One important factor here is K, which represents the number of nearest neighboring locations considered during imputation. They found that increasing the K improves the model performance. Next, they also discovered that by including socio-economic factors, the model makes even more accurate predictions. Furthermore, compared to traditional models like Poisson method, SIKL's estimations are closer to the actual incidence rate.
The conclusion of this journal is first, incomplete data in public health surveillance is a significant challenge. It complicates the effective detection and prevention of epidemics. Second is that the journal introduced spatial temporal imputation via kernel-based learning, STIKL, which is a new method that infers missing data by considering location-specific and dynamically changing disease-related risk factors. Third is extensive experiments by using both real-world malaria surveillance data and a synthetic datasets validate the effectiveness and accuracy of the STIKL method. Lastly, STIKL method outperforms existing algorithm and it provides more accurate and meaningful results for managing incomplete data in public health surveillance.
Next, let's take a look at the limitations of this method. STIKL requires enough measurement data to learn spatial temporal correlations effectively. In regions with very limited data, its performance might drop. Additionally, it does not yet consider other useful structures such as local smoothness, local similarity structures, and lowering structures.
From this journal, the real-world application that we can apply is disease monitoring and prediction, where we can do early detection and prediction of epidemics for various infectious disease and help track, spread, and inform timely interventions. Second is public health resource allocation, where we can optimize the deployment of essential resources such as medical supplies and personnel by identifying disease hotspots. Lastly is environmental monitoring, where this can be applied in areas such as predicting air quality by filling in missing sensors data to inform public health measures. So the future works that we can see is that we can develop more advanced models to learn shared patterns across diverse spatial temporal datasets and improve generalization and efficiency, and lastly incorporating diverse data sources and include social, economic, and environmental factors to provide a more holistic understanding of health and disease.